Welcome to KJR SummaryCast. SummaryCast provides audio summaries of KJR articles created using an in-house AI tool with editorial or author review. For full details, please refer to the original article. Welcome to SummaryCast.
Welcome! Today we're digging into a paper that aims to clean up a promising but often noisy imaging signal used for evaluating brain tumors. The paper is titled Fluid Suppression Techniques Combined with Amide Proton Transfer Weighted Imaging for the Evaluation of Adult-Type Diffuse Gliomas.
And this was just published in the latest issue of the Korean Journal of Radiology.
Right. So, to really appreciate what this paper is doing, we have to start with the challenge of imaging gliomas. Standard structural MRI is the workhorse, of course, but things like contrast enhancement don't always reliably tell you the tumor's grade or molecular subtype.
Which is why there's so much interest in advanced functional techniques that can give us a look under the hood at the tumor's biology.
Exactly. And that brings us to the core technique here, amide proton transfer weighted imaging, or APTW. It falls under a broader category of methods called chemical exchange saturation transfer, or CEST.
And what does it measure in practical terms?
At a high level, it gives us a window into tissue metabolism. It's tuned to detect the signal from amide protons, which are found in mobile proteins and peptides within cells. So, more signal generally means more cellular proliferation and metabolic activity.
Which has shown real promise for things like tumor grading, classifying molecular subtypes, and even assessing treatment response.
It has, but it comes with a significant catch. A well-known artifact can really throw a wrench in the works.
And that artifact is fluid.
That's the central problem this paper tackles. Areas with a lot of fluid, like cystic changes or regions of liquefactive necrosis within a tumor, can produce a markedly elevated signal on APTW imaging.
A falsely high signal. So you might look at a necrotic core and mistakenly think it's a region of super high metabolic activity.
Precisely. It creates these bright spots that aren't necessarily related to the tumor's true biology, which can obviously mislead an assessment and limit the technique's broader clinical application. So the research question is quite clear.
Can we get rid of that confounding fluid signal to produce a cleaner, more diagnostically useful image?
That's the entire move here. The authors took a retrospective cohort and applied 3 different processing methods to their APTW data. The first is just the conventional standard approach.
The baseline, and the other 2 are fluid suppressed.
Yes, the first they call FS-APTW. It's a more direct heuristic method for suppressing the fluid signal. Think of it as a relatively simple noise filter.
Okay, and the second?
The second is more advanced. It's called spillover-corrected FS-APTW, or SCFS-APTW. It's built on a more robust theoretical foundation and is designed not just to suppress fluid, but also to correct for other spillover effects from the magnetic field that can contaminate the signal.
So 3 methods, the conventional baseline, a standard fluid suppression, and an advanced spillover-corrected fluid suppression.
You got it. They applied these to a cohort of 117 patients with newly diagnosed adult-type diffuse gliomas, all of whom had a preoperative 3T MRI that included the necessary APTW sequence.
117 patients is a pretty solid number for this kind of specialized imaging study. What was the breakdown of tumor types?
It was a good mix. According to Table 1, they had 52 patients with IDH wild-type tumors, which included 45 glioblastomas and 7 other tumors classified as NEC, or not elsewhere classified, and 65 patients with IDH mutant tumors.
And within that IDH mutant group,
there were 46 astrocytomas and 19 oligodendrogliomas. So they had the key subtypes needed to test their hypotheses.
And how did they analyze the images? Consistency can be a real issue when you're drawing regions of interest.
They were quite rigorous on this point. 2 neuroradiologists, each with 5 years of experience, independently performed the ROI segmentation, and they were blinded to the final histology.
And did they agree?
The inter-observer agreement was excellent, with intra-class correlation coefficients ranging from 0.957 to 0.993. That gives you a lot of confidence in the underlying measurements.
I see they also used both mean values and the 90th percentile, or P90, from the ROIs. Why both?
That's a clever methodological choice to handle tumor heterogeneity. The mean value gives you a sense of the whole region, but gliomas are not uniform.
So the P90 metric is meant to capture the hotspots.
Exactly. It approximates the maximum value you'd find in those hotspots, but it does so in a way that's more stable and reproducible between different observers.
Got it. A robust way to capture the most aggressive parts of the tumor. Okay, let's get to the results. First and foremost, did the fluid suppression actually work?
It did, and the effect was stark. Table 2 lays out the signal intensities in the necrotic and cystic regions for each technique.
What are the numbers?
With conventional APTW, the mean signal in these fluid-filled areas was 3.56, a very high artifactual signal.
Okay, that's the baseline problem.
With the first fluid suppression method, FS-APTW, that signal was more than halved, dropping down to 1.74.
That's a huge reduction. And the advanced spillover corrected method?
The SCFS-APTW pushed it down even further to a mean signal of just 1.11, a really profound suppression effect.
So the techniques do exactly what they claim to do, but what about in normal appearing tissue? You don't want a correction that distorts the healthy baseline.
Great question. They looked at the contralateral normal appearing white matter, or CNAWM. There, the signal changes were statistically significant but very small in magnitude. It barely budged.
Which is what you want to see. It suggests the correction is specific to the pathological tissue with high water content and isn't just blanket suppressing the signal everywhere.
Precisely. So, with the technical proof of concept established, let's get to the main event. Diagnostic performance. How did these cleaner signals fare in predicting IDH mutation status?
A critical task in glioma diagnosis.
It is. Looking at the area under the ROC curve, or AUC, from Table 5, the conventional APTW method started with a respectable AUC of 0.801.
A good, but not perfect starting point.
Right, but both fluid-suppressed methods improved on it. FS-APTW pushed the AUC up to 0.834.
And the advanced SCFS-APTW performed the best?
That's right. It achieved the highest AUC of 0.846. Breaking that down, it had a sensitivity of 84.6% and a specificity of 74.5%.
So you get a clearer, more effective discriminator of this key molecular marker. Now, the authors do note that while the trend is positive, the improvement over the conventional method didn't reach statistical significance after Bonferroni correction.
A fair point. It's a consistent but statistically modest improvement for IDH status. The story gets even more compelling, though, when we look at differentiating the glioma subtypes.
Okay, where did the fluid suppression make the biggest difference?
The most striking result was in differentiating glioblastomas from oligodendrogliomas.
That can be a very challenging distinction to make based on imaging alone.
It can, and with conventional APTW, the performance was quite poor. The AUC was only 0.690.
That's barely better than a coin flip. Not a tool you'd want to rely on.
Not at all. Its sensitivity was only 52.6%. But watch what happens when you apply fluid suppression. With the 90th percentile of the spillover-corrected SCFS-APTW signal, the AUC climbed all the way to 0.832.
From 0.69 to 0.83, that is a massive lift. Let's look at the sensitivity and specificity.
That's where you see the change. The sensitivity jumped from 52.6% to 84.2%, with a specificity of 80.0%. That's the kind of improvement that could genuinely change diagnostic confidence in practice.
Why do you think that specific comparison benefited so much?
The paper suggests a very plausible reason. Glioblastomas are notoriously necrotic. That large fluid component heavily contaminates the conventional APTW signal. Oligodendrogliomas are typically less necrotic. So when you strip away that artifact, the true biological signal of the viable glioblastoma tissue stands out much more clearly, making the distinction far easier.
That makes perfect sense. What about the other comparisons? Were they able to distinguish astrocytomas from oligodendrogliomas?
Unfortunately, no. That remains a tough nut to crack for APTW imaging. None of the three methods could reliably separate them. The AUCs were all hovering around 0.55.
Still a coin toss, so it's not a magic bullet for all subtype classifications, but it provides a powerful boost for a specific, challenging one. The final piece was proliferation.
Right, the correlation with the Ki-67 labeling index. They found a moderate positive correlation across all the APTW metrics, which is biologically expected. A higher signal means higher proliferation.
Did one of the fluid-suppressed techniques show a stronger link?
Yes, once again, the spillover-corrected SCF-SAPTW had the tightest relationship. It demonstrated the strongest correlation with Ki-67 with a Spearman coefficient of 0.451.
So across the board, IDH status, subtype differentiation, and proliferation, the trend is consistent. Removing the fluid artifact seems to provide a more accurate reflection of the underlying tumor biology.
That's the core finding. The analysis strongly suggests that by reducing contamination from fluid and necrosis, the remaining APTW signal becomes more specific and more biologically meaningful.
And what's particularly compelling here is the implementation. You mentioned these are post-processing methods.
That's right, and it's a critical advantage. These are not new MRI sequences that require different hardware or more scan time. They're calculations performed on the raw data from a standard APTW scan after the patient has left the scanner.
That makes them highly feasible for integration into a clinical workflow. No extra burden on the patient or the schedule.
Exactly. Which brings us to the limitations because no study is perfect.
What's at the top of the list?
First, this is a retrospective single-center study. While the cohort size is decent, the findings really need to be validated in a larger multi-center setting to ensure they're generalizable.
That's a standard but important caveat. What about the imaging protocol itself?
Good point. They used a 2D single-slice acquisition for the APTW scan.
Which could theoretically miss the most aggressive part of a heterogeneous tumor.
It could. The authors argue that previous work shows comparable performance between 2D and 3D, but a full volumetric acquisition would certainly be more robust.
And there's another technical detail worth mentioning. The core metric is still based on asymmetry analysis, right?
It is. So even though they've done a great job suppressing the fluid signal, other confounders like nuclear Overhauser enhancement can still contaminate the signal.
So it's an important step, but it doesn't completely purify the signal. It's removing the biggest source of noise, but not all the noise.
You nailed it. It's a significant refinement, not a final solution to all of the technique's inherent challenges.
So let's land this. What's the bottom line takeaway for a radiologist interested in advanced neuroimaging?
The bottom line is that these fluid suppression techniques are an effective, practical, and readily available way to improve the diagnostic utility of APTW imaging in gliomas. It's a software-based enhancement, not a hardware one.
And while the improvements are modest in some areas, they provide a significant, clinically relevant boost for specific, difficult diagnostic tasks, most notably telling a glioblastoma from an oligodendroglioma.
Precisely. It's a very elegant example of how smarter post-processing can sharpen an existing imaging tool, making the information it provides more reliable and ultimately more useful for patient care.
A tidy and practical refinement with real potential.
It is. The next logical step would be to test these cleaner metrics in a prospective trial, perhaps combining them with radiomics to see if predictive power can be pushed even further.
That concludes this episode of SummaryCast.
Thank you for listening.